Everybody, we are ready for 7.5, solving trigonometric equations. So here's some things to keep in mind while you're solving some trigonometric equations. Number one, decide whether the equation is linear or quadratic in form in order to determine the solution method. If there's only one trig function present, see if you can get that trig function by itself or just solve for that function. If more than one trigonometric function is present, you might want to rewrite it so that one side equals 0 and see if you can factor out one of the trig functions and you can use the zero factor property. If it's in quadratic form, but it's not factorable, remember we also have the quadratic formula. You may want to use U substitution for some of these. And also try using some of our identities to see if you can substitute those in and make the equation easier to use. Sometimes you have to maybe square each side of the equation first if it is going to look like one of those identities. And if that's the case, whenever you multiply both sides of an equation by a variable, you want to check that you didn't throw in some extra solutions that does not work with the original. So also with your answers, be sure that you always check to make sure that they are in the interval that they're asking you for. So let's do a few examples. Example 1 is an example of a linear equation. We have 3 tangent theta minus the square root of 3 equals 0. And we're looking for all exact solutions on the interval from 0 to 2 pi. Now, we always want to put our answers in exact form if we can. That means leaving it as a square root instead of having to round the number in our calculator. So if they're using the word exact, that definitely means we should be coming up with exact answers. If it just says find all solutions, some of them may be exact and other ones you have to use your calculator and find a decimal approximation. So for A, let's get tangent by itself. So we would get 3 tangent theta, we would add that square root of 3 to the other side, divide both sides by 3, and we get the square root of 3 over 3. Now, you may not recognize that tangent equals the square root of 3 over 3 at 2 places, where theta is pi over 6 and 7 pi over 6. In other words, in the first quadrant and again in the third quadrant. So if you still struggle with that, you can also use your inverse or arctangent functions to find them, or think of it in terms of sine theta over cosine theta. This is the same thing as a 1/2 over rad 3 over 2, which would give us 1 over rad 3, which is rad 3 over 3. So sometimes we can work it backwards as well. So we're given pi over 6 and 7 pi over 6. Those are in the interval 0 to 2 pi. But then in part B, they're wanting us to find all exact solutions, and they didn't give us an interval. So that means we need to show how often these solutions repeat. Recall that our period for tangent is pi, or it would be pi divided by b if you had something being multiplied by that angle in there. But since there's nothing, it's just a theta, then every pi units, we're going to hit that same value. So to represent all solutions in perpetuity, we would start with the one we found, pi over 6. And then if we add every kth pi, where k is an integer. In other words, -1 pi, -2 pi, or 0 pi, 1 pi, 2 pi, 3 pi. Every time we go around, we would hit that same place on the graph. But we also have 7 pi over 6, which if you think about it, is also pi units. So if we're hitting everything in the circle, this would include pi over 6 plus 1 pi, which would be 7 pi over 6. So it's already included here. We don't have to list it twice. Our next example is an example of using a zero factor property method. So notice we are having not only cosine, but also cotangent. So you have to be careful. Sometimes we read it as cosine, but notice there's a T instead of an S. So if we added that cosine theta to the other side, then we can factor out a cosine theta. and use our zero property. In other words, we have two factors being multiplied, this factor and this factor. So either cosine of theta equals 0 or cotangent of theta plus 1 equals 0. Well, for cosine theta equals 0, we know that x value or cosine value equals 0 in two places, at pi over 2 and at 3 pi over 2. If we solve for cotangent theta, it equals a -1. And remember, that's cosine over sine. So in order for it to be -1, they would have to not only equal each other, so we're looking at some multiple of pi over 4, but their signs also has to be opposites, one positive and one negative. So that means we would be here in quadrant 2 or quadrant 4. So that would be 3 pi over 4 here or 7 pi over 4 there. So we have 4 possible angles. We have pi over 2, if we were to put them in order, pi over 2, 3 pi over 4, 3 pi over 2, and 7 pi over 4. So I know your homework can be a little tricky, so pay attention if they ask you to put them from smallest to largest or round to 4 decimal places. We always want to be careful. Example 3 is another zero factor property method, but notice everything's in terms of signs. We want to see if we can actually factor this. For some of us, it may help to write this in terms of a variable instead of sign. You're allowed to do that. We can let u be sine of x, and if we substitute that in, we get 3u squared minus u minus 2 equals 0. And now we see it a little bit better as a quadratic. We want to see if it's factorable. Luckily it is. We would get 3u plus 2 times u minus 1 equals 0. Set each factor equal to 0. So we get u equals a -2/3 and u equals 1. Well, again, we're not done because u equals sine of x. So if we plug our sine of x back in, -2/3 or sine of x equals 1. Well, only one of these values are we familiar with, and that's where sine of x equals 1. That's at pi over 2. So we know this guy equals pi over 2. That's an exact answer. But -2/3 isn't a value that we can find on the unit circle that we're familiar with. So we're going to have to use our inverse function, sine inverse or arcsine of a -2/3. So we can go to our calculator. So in our calculator, remember the interval they gave us was from 0 to 2 pi. So let's make sure we're in radians. And we're not, we're in degrees. So let's go down, highlight radians, hit enter. And then we can quit out of that. And now we can do our second function sine to get our arcsine or sine inverse. The input value was a -2/3. And that gives us a -0.729727. So let's write that. So here's the value that we got in our calculator, a -0.72727. But notice that's not in our interval that was given to us. So let's draw that and get an idea of where it is. So if we're down here somewhere, and this angle here is a -0.72973, we'll say. We want to find the two equivalent that will give us the same sine value, the same negative sine value between 0 and 2 pi. So we need to use our reference angles. Well, sine, since it's our y value, is negative down here in the 3rd and 4th quadrant. So that angle and its other reference angle here, both of those angles will be two possible solutions in our interval. So the first angle from standard position to here would be pi plus the 0.72973. So notice I'm carrying it out past the 4 decimals because we're also going to add pi to it. And you want to be very careful about rounding too quickly or too short, because it may round to higher numbers in the long run or smaller numbers in the long run. So if we put that into our calculator, we get approximately 3.8713. And then on the second one, we want this angle all the way to here. So the easiest way to find it would be 2 pi minus the 0.72973, which is approximately 5.5535 if we're carrying it to 4 decimal places. So we have found 3 angles or 3 x values that work. One of them is an exact value and the other 2 are approximations. In example 4, we're looking for all solutions for this equation. Now, it doesn't say that it's exact and it didn't give us an interval. So we have to represent every single one using that k. Let's find out what we've got here. If we distribute that cosine, I know it's factored, but it's not set equal to 0. So it looks like we're going to deal with a quadratic again. If we distribute, we get cosine squared x plus 2 cosine x. And then if we subtract 1 from both sides, we get a nice quadratic equal to 0, but it's not factorable. So we're going to have to use our quadratic formula. Again, our a is the 1, b is 2, c is -1. So remember our quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. But this time it's not just x. Our unknown is the cosine of x, okay? So that means we would have the cosine of x equals the opposite of our b plus or minus the square root of our b squared minus 4 times our a times our c all over 2 times our a, which is 1. So that would give us -2 plus or minus the square root of 4 plus 4. So that's the square root of 8, all divided by 2. I made that square root a little long there, which is a -2 plus or minus 2 rad 2 all over 2. And remember, we cannot reduce with that 2 unless everybody gets reduced by that 2. Both the -2 and the 2 rad 2 are above that denominator. So that means we have a cosine of x, which gives us a -1 plus or minus the square root of 2. So we have to find 2 different values. Now, notice what happens when we do cosine inverse of -1 plus the square root of 2 as one value, and cosine inverse of -1 minus square root of 2. Something's kind of unexpected or maybe expected might happen there, and we'll talk about that when we get to it. So let's focus on the first guy. Let's go to our calculator. So let's do cosine inverse of -1. Remember, you want to use the negative down here by the enter. -1 plus square root of 2. Be sure that parentheses in the right place there. And so when we hit enter, we get approximately 1.1437144. Great, that lands in quadrant 1. But notice what happens when I put the other version in. I'm going to hit second function entry to copy what I had before, and I'm just going to change that plus sign to a minus sign. So notice I got to use the minus symbol here, not this guy. It is subtraction. And look what we get. Oh, it's a bummer, right? Value entered not allowed in the function or command. So when we go back, notice the value -1 minus the square root of 2 is outside the interval -1 to 1. Remember, cosine and sine only go from -1 to +1, unless there's been some sort of, shift, which there's not, because we solved for the cosine by itself. So the number is outside our domain. So let's go back to our notes. So this is the one value that we had on our calculator, and this guy doesn't work. So you may want to make yourself a note that that value right there is not between -1 and 1. So it didn't work, not in our possible domain for x. But remember, we want to find all possible solutions. So again, this value here, cosine inverse, is always between your first and second quadrants. And that value is positive. -1 plus the square root of 2 is larger. So he's going to be up in here somewhere. 1.14, let's see, 371774, up there somewhere. Where else is our cosine positive? Down in this quadrant here. So this angle here and this angle here are both that value. So we know that x is one of those values. And again, we can round it to 4 decimal places, 1.1437. And cosine has a period of 2 pi. So 2k pi, where, and remember that symbol from before, we can use that, where k is an integer. But then we also have to find that possible solution in the 4th quadrant. So if we were to think of this one all the way around, probably easiest to find it to take the 2 pi and then subtract the 1.143717774. So if we put that in our calculator, we get approximately 5.1395. So our other x value would be 5.1395 plus 2k pi, where again, k is an integer. So remember, when you're having to use the inverse function, cosine inverse or arc cosine or sine, to find a value, it's only going to give you the value in one of 2 quadrants. So we may need to find an equivalent value in another quadrant. So you always have to look. In example 5, they're wanting us to find all exact solutions for this equation, 2 cosine of x over 2 minus the square root of 2 equals 0. Part A is over an interval, 0 to 2 pi, and part B is all exact solutions, and they did not give an interval. Okay, so it's just to remind us that they may ask us just for a finite number of answers, or they may ask us to represent everything, and that's where the K and the period comes in. So one thing that might help, again, is to let U equal our x over 2. You don't have to in these, but sometimes it's easier for some people to work with it that way. So we would get 2 cosine of U. I'm going to go ahead and add that square root of 2 to the other side. So we get cosine of U equals the square root of 2 divided by 2. Now, cosine is positive in 2 quadrants. That's in quadrant 1 and in quadrant 4. So that would be at where U equals pi over 4 and where U would equal 7 pi over 4. And so far, both of those are in our intervals 0 to 2 pi. But remember, U is not what we're solving for. Let's substitute back in. So x divided by 2 equals pi over 4. And x divided by 2 equals 7 pi over 4. So now when we solve for x, we're going to multiply both sides by 2 in both of those equations there. So we would get x equals pi over 2 and x equals 7 pi over 2. Well, this is definitely within our interval 0 to pi, but this guy here is not in our interval between 0 and 2 pi. So that guy's not going to work in part A. So when you substitute back in, be sure that you're solving just for the variable and not for still that variable divided by 2 or multiplied by 3. Now, in part B, it can be a little tricky because in part B, we're looking for all exact solutions. 2 things. First of all, what's the period of that function? The period of that function is 2 pi, but 2 pi divided by the b value. Remember, the b is what's being multiplied by our x. Well, if we go up here to the cosine, this is 2 cosine, technically 1/2 times x minus the square root of 2. So this 1/2 is actually going to change our period. So we're going to divide this by the 1/2. So that means for the cosine of x over 2, it's going to repeat every 4 pi. Our first x value, which is pi over 2, we're going to add plus 4k pi, where k is an integer. But also, remember when we talked about the 7 pi over 2 not being on the interval from 0 to 2 pi? So even though the 7 pi over 2 was not in the original interval, it is in the domain for part B, all real numbers. 7 pi over 2 plus 4k pi, where k is an integer. So when we are dividing those by 2, we would get the pi over 4 and the 7 pi over 4 in this quadrant 1 and in this quadrant 4. Find all exact solutions for the equation cosine 2x equals sine x on the interval. Now this one is where a trigonometric identity might come in handy, because I can't change cosine 2x to sine x using Pythagorean. I can't factor it out because one has an angle, one is a double angle. Since it's easier to work with one trigonometric function instead of two, I would want to substitute in the version of the cosine of 2x with 1 minus 2 sine squared x equals sine x from the double angle formulas. Now it's more of a quadratic. I'm going to move everything to the right and set it equal to 0. So we'll get 2 sine squared x plus sine x minus 1. And that's factorable. You can use substitution. If not, you can always factor it with the signs. That would be 2 sine x minus 1 times sine x plus 1. You can set both of those factors equal to 0. So in the first equation, we would get sine x equals a positive 1/2. There's 2 places where sine of x equals 1/2 on 1 revolution between 0 and 2 pi. And that is at pi over 6, 5 pi over 6, quadrant 1 and quadrant 2. The second equation, when we solve it, we get sine of x equals -1, and there's only one place where it equals -1, and that is at 3 pi over 2. So we get 3 possible solutions for our x. 7 is another example of a trigonometric identity substitution. We can do some other substitutions to try to get them in with the same cosine and sine values, but what you may notice is with cosine squared theta minus the sine squared theta, that is actually a double angle formula for cosine. So if we factored out the 2 just with those first 2 functions, then we can substitute in and get 2 times the cosine of 2 theta plus the square root of 2 equals theta. Then we can solve for the cosine of 2 theta. So we get cosine of 2 theta equals a negative square root of 2 over 2. Remember, cosine is your x values, so it is only negative in quadrant 2 and quadrant 3. And it equals the negative square root of 2 over 2 at those multiples of 45 degrees. So that would be at 3 pi over 4 and at 5 pi over 4. So we get 2 theta equals 3 pi over 4 and 2 theta equals 5 pi over 4. We don't want 2 theta, we want just theta. So divide both sides by 2 and we get 3 pi divided by 8 and we get 5 pi divided by 8. But we want to be sure that those are the only angles that work, okay? So remember, theta has to be between 0 and 2 pi. We are working with 2 theta. So we also want to consider 2 theta could be 3 pi divided by 4 plus 2 pi. We want to see if that is also within our interval. Because notice it will hit the same spot every time. So 3 pi divided by 4 plus 2 pi, divide everything by 2. We get 3 pi divided by 8 plus pi. And that pi is the same thing as 8 over 8. So that gives us 11 pi over 8. That is still less than 2 pi. It's less than 16 pi over 8. So that is a third angle that works. And then we can try it with this guy as well, where 2 theta would be 5 pi over 4 plus 2 pi. Go out another period. Divide everything by 2. We get 5 pi divided by 8 plus 1 pi, which would be 8 over 8 pi. So that would be 13 pi over 8, also still within our interval. So we get a theta equals 13 pi over 8. If we kept going another 2 pi, notice we're already getting pretty close. We're at 11 pi and 13 pi, both over 8. 16 pi over 8 would be our max. So we know we can stop right there. We have to be careful whenever we're dealing with double angles or even half angles to make sure that if we went out another period, that we're not missing some of those extra answers. All right, that's it for me. Thanks for watching. Bye.